In section 7.6, we discussed the channel capacity in the presence of feedback. Feedback is commonly used in practical communication systems for correcting possible errors which occur during transmission. Daily examples of feedback in communication includes phone conversation and also classroom teaching. In data communication, the receiver may request a packet to be retransmitted if the parity check bits received are incorrect. This is called automatic repeat request, or ARQ in short. The transmitter can at any time decide what to transmit next based on the feedback so far. The question is, can the use of feedback increase the channel capacity? Surprisingly, the answer is no for the discrete memoryless channel, even with complete feedback. This means that even the transmitter knows exactly what has been received by the receiver so far, it is not possible to transmit information through the channel reliably at a rate higher than without feedback. In the remaining of this section, we are going to see why this counterintuitive result holds. Definition 7.18 is the definition of a feedback code. An NM code, recall that N is the block length of the code and M is the size of the message set, with complete feedback for a discrete memoryless channel with input alphabet X and output alphabet Y is defined by the encoding functions Fi from the message set 1 to up to M times the output alphabet Y to the power I minus 1 to the input alphabet X, where I is from 1 up to N, and a decoding function G from the output alphabet Y to the power N to the message set 1 to up to M. We are going to adopt the following notations. We use bold Y sub I to denote the sequence Y1, Y2 up to Yi, and Xi to denote Fi of W and Y sub I minus 1. Here, Xi is the symbol to be transmitted through the channel at time I. The function Fi is the encoding function for the ith transmission, which depends on W, the message to be transmitted, and Y sub I minus 1, the first I minus 1 symbols received by the channel. Because of this code uses complete feedback. Here is the schematic diagram for an NM code with complete feedback. At time I, the symbol Xi is transmitted through the channel, and the symbol Yi is received and fed back to the encoder. This is the dependency graph for a channel code with feedback, which is equivalent to the factorization Q of W, X, Y, and W hat equals Q of W times the product from I equals 1 up to N, Q of Xi given W and Y sub I minus 1 times the product from I equals 1 up to N, P Yi given Xi times Q of W hat given Y, where this factorization is valid whenever the conditional events have non-zero probabilities. Definition 7.19 is the definition of a rate R being achievable with complete feedback. A rate R is achievable with complete feedback for a discrete memoryless channel Py given X if for any epsilon greater than 0 there exists for sufficiently large N an NM code with complete feedback such that 1 over N times log M, that is, the rate of the code, is at least R minus epsilon, and at the same time, the maximal conditional probability of error is less than epsilon. Definition 7.20 is the definition of the feedback capacity. It says that the feedback capacity, C feedback, of a discrete membrane-less channel is the supremum of all the rates achievable by codes with complete feedback. Proposition 7.21 says that the supremum in the definition of the feedback capacity in definition 7.20 is indeed the maximum. The proof follows directly from definition 7.19. Please see the textbook for details. We remark that since a channel code without feedback is a special case of a channel code with feedback, because the code can ignore the feedback even if it is available, the feedback capacity is at least equal to the capacity without feedback. We now prove lemma 7.22, which says that for all I, W and Y sub I minus 1, Xi and Yi forms a Markov chain. We first note that the Markov chain W, X sub I minus 1, Y sub I minus 1, Xi, and Yi holds because the channel is membrane-less. Note that in the Markov chain in lemma 7.22, the set of random variables on the left-hand side is a subset of the set of random variables on the left-hand side of this Markov chain. Thus, intuitively, the Markov chain in lemma 7.22 should hold. The proof goes as follows. From the Markov chain in step 1, we have that the mutual information between W, X sub I minus 1, Y sub I minus 1, and Yi, conditioning on Xi, is equal to 0. For the ease of visualization, we temporarily cover Xi, the conditioning random variable. By means of the chain rule, we can expand this mutual information into the sum of two mutual informations. First, the mutual information between W, Y sub I minus 1, and Yi, and second, the mutual information between X sub I minus 1, Yi, conditioning on W and Y sub I minus 1. Now we restore the conditioning random variable Xi. Because the sum of these two mutual informations is equal to 0, and the mutual information is always non-negative, we see that both mutual informations are equal to 0. In particular, the first mutual information, namely I, W, Y sub I minus 1, and Yi, given Xi, is equal to 0, which is equivalent to the Markov chain W, Y sub I minus 1, Xi, and Yi. This proves the lemma. We have seen that the feedback capacity is at least equal to C, the capacity without feedback. Now we prove that the feedback capacity is also less than or equal to C. So from this, we can conclude that the feedback capacity is actually equal to C. Consider any code with complete feedback. Consider log M equals entropy of W because the message is chosen uniformly from the message set, and HW is equal to IWY plus HW given Y. For the first term, IWY can be written as HY minus HY given W. And HY given W can be written as summation I equals 1 up to n, HYI given Y sub I minus 1 and W, where this is an application of the chain rule. Now we insert the random variable Xi in the conditioning in the ith term of the summation. This is valid because in a feedback code, xi is a function of w and y sub I minus 1. In other words, by inserting xi, we do not add any new information in the conditioning. Now by lemma 7.22, because yi is independent of w and y sub I minus 1 given xi, we can eliminate y sub I minus 1 and w in the conditioning in the ith term. And so, we have hy minus summation I equals 1 up to n, hyi given xi. By the independence bound, hy is upper bounded by summation I equals 1 up to n, hyi. Now combining hyi and minus hyi given xi, we have I, xi, yi, the mutual information between the input and the output of the channel at time I. And by the definition of C, each of these mutual informations is less than or equal to C. And so we obtain the upper bound n times C. Now for the second term on the right hand side in step 2, we have hw given y equals hw given y and w hat. This is valid because w hat, which is the estimated message, is a function of the received sequence y. By removing the sequence y from the conditioning, we obtain the upper bound hw given w hat, because conditioning can only reduce entropy. Now hw given w hat is very close to 0 for reliable communication. So from step 2, we have log m equals iwy plus hw given y, where iwy is less than or equal to n times c, and hw given y is very close to 0. And therefore, we obtain that log m is less than or equal to nc asymptotically. Formally, we apply Farnell's inequality to upper bound hw given w hat. Upon filling in the epsilons and deltas as in the proof of the converse of the channel coding theorem, we conclude that R is less than or equal to C for any rate R achievable with complete feedback. Here are some remarks regarding the feedback capacity. Although feedback does not increase the capacity of a discrete memoryless channel, the availability of feedback often makes coding much simpler. I urge you to go through the example for a binary erasure channel in example 7.23. In general, if the channel has memory, feedback can increase the capacity.